The first plenary talk from today's 3 plenary talks is entitled Silicon Technology and Solutions for the Data-Driven World by Kinam Kim. Dr. Kinam Kim is the president of semiconductor business in Samsung Electronics since 2014 and was the president and CEO of Samsung Display from 2012 to 2013 and president of Samsung Advanced Institute of Technology and CTO of Samsung Electronics from 2010 to 2012. He is also the chair of Korean Semiconductor Industry Association since 2014. He received his BS in EE from Seoul National University, MS degree in EE from KAIST, and PhD in EE from UCLA. Dr. Kim has a key contributor in the advancement of DRAM and memory technologies over the past 3 decades. He has been personally responsible for the development of the 128 kilobit to 4 gigabit DRAMs, 2 gigabit to 32 gigabit NAND flash, among other technologies. He is a foreign member of U.S. National Academy of Engineering, an IEEE Fellow, a member of both National Academy of Engineering and National Academy of Science of Korea. Please welcome Dr. Kim.
Thank you, Professor Yu, for your kind introduction. Good morning, ladies and gentlemen. It is a great pleasure for me to be here, and I would like to thank the organizers of ISSCC for inviting me to present a plenary talk. In next 40 minutes or so, I hope to share with you the exciting development of silicon technologies and also solutions that are enabling data-driven world. This is the content of my presentation. I will start with brief introduction of data-driven world, followed by enabling technologies, which are silicon technology, advanced package, and solution technologies for small chips. And finally, I will conclude with data security in the data-driven world. Today, you are living in an era where the amount of data is fast increasing, which could be best described as the data-driven world. It is difficult to say the exact time when data-driven era began. Let's look at some statistics and predictions, which might provide some insight. As you can see on the screen, in 2002, when the world population was 6.6 billion, the number of connected things was about 500 million. By 2008, the number of connected things surpassed the population. By 2020, there will be more than 50 billion connected things. All these connected things will generate a lot of data, some of which will end up in data centers. As the amount of data produced rapidly increases, so does workload of data centers. As you can see from the graph, blue region is the amount of data produced, which during the past 3 years has increased by a factor of 3. The green plot shows power consumed in these centers, which increases at a similar pace. On the other hand, data center space is increasing at a much slow rate. This large gap could be compensated by a faster CPU and higher density that consumes less energy. In other words, it is the role of silicon technology to fill this gap. Silicon technology will be able to fill the gap through technology scaling. Advanced packaging and chip solution will be added to fill the remaining gap. All these technologies could maximize performance and low power small chips, which will be the engines of data-driven world. But foremost, all innovation starts from silicon technologies. Silicon scaling has followed Moore's law, which states number of transistors in an IC doubles almost every 2 years. This is true for logic as well as memory devices. This law still holds true even to this day. Here in the graph, we have plotted number of transistors inside a chip per unit area as a function of years. It shows it doubles about every 2 years. There is no reason to believe this trend will stop anytime soon. According to fundamental physics, the limit for transistor scaling is 1.5 nanometer at room temperature. Device physicists tell us that we can have properly working CMOS transistors down to 3 to 5 nanometer. In fact, we Samsung have demonstrated a properly working 3.8 nanometer CMOS transistors, as you can see right-hand side panel. This work was presented at 2009 Verasite Technology Symposium. Recently, there have been many discussions on silicon scaling limit. But personally, I believe that you will have no problems going below 5 nanometer. Feynman once said, there's plenty of room at the bottom. We have already started lay foundation to build in the room. On the other hand, manufacturing technology is also pushing its limit. The state-of-the-art EUV lithography is capable of resolving 13 nanometer. By combining EUV with already proven quadruple patterning technology, it is possible to print 3.25 nanometer patterns in the future. But we are currently able to print only 8 nanometer half pitch with existing resist materials, which is far above the resolution limit. In order to better serve EUV technology, new resist materials will need to be developed. Now, let us look at building blocks of small chips, which are logic and memory technologies. This slide shows the evolution of logic technology over the past decade. In 45 nanometer node, high-K dielectric metal gate was implemented in order to increase density and improve performance. At 20 nanometer node, 3D transistor structure, such as FinFET, was applied. The wrap-around gate structure of FinFET provides better electrical control of the channel. Thus, it helps in reducing leakage current and overcoming short channel effect. All these technologies have been implemented to boost PC performance, which years later were also adopted in mobile devices. However, because high demand for mobile computing, technology adoption time gap is narrowing. For instance, in mobile devices, 45 nanometer technology was adopted 2 years later than PCs. But for 14 nanometer, the gap narrowed down to 3 months. Mobile application will probably lead in 10 nanometer adoption instead of PC applications. Samsung has started mass production of 14 nanometer FinFET for mobile applications. As you can see in the picture, Samsung already has secured 10 nanometer FinFET process. This beautiful FinFET profile means excellent device characteristics. We anticipate FinFET will be mainstream beyond sub-10 nanometer. There are many other device options, gate-all-around, nanowire FET, tunnel FPD, and others for minimizing leakage current, and alternative channel materials to enhance mobility. All these device options and materials will be able to push large technology to its limit. But one thing I would like to point out here is that whatever the structure and materials we choose, it must be well matched with existing silicon infrastructure. Otherwise, it might not be economically viable. DRAM scaling has been possible through innovation in 2 key elements, which are cell capacitor and cell transistor. The capacitor's aspect ratio had to be increased in every generation, which was possible through innovation in processing small and deep capacitor holes. Additionally, in order to reduce EOT, EOT means equivalent oxide thickness, high dielectric constant material had to be developed, which currently is zirconium oxide-based multilayers. In 10 nanometer node, in order to conserve the integrity of capacitor structure, a stacking stream will be needed. On the other hand, cell transistors have evolved towards reducing leakage current. Until 40 nanometer node, junction leakage current had to be overcome with recessed channel cell transistor. In sub 40 nanometer node, gate-induced drain leakage problem due to the overlap region between gate and source drain was resolved by buried waterline scheme. In 10 nanometer node, in order to solve intercell disturbance, you may have to implement gate all-around structure as shown at bottom corner. By the way, 15 years ago, I had presented an IEEE invited paper where I said DRAM cell capacitor limit would be 20 femtofarad. But today, as you can see, it is already 10 to 15 femtofarad, and it will be going down. This tells me once again, there is no limit what engineers can do. Our latest DRAM technology stands at 20 nanometer, which Samsung mass-produced for the first time in the world last year. 20 nanometer mobile, server PC, and graphic DRAMs are currently available as shown in left panel. The success of 20 nanometer technology comes from we maintain the ratio between B-line and storage capacitance as that of previous generation. By the way, CV/CS ratio is the key design parameter for DRAM cell operation. Storage capacitance inevitably gets reduced with scaling, which could be partially compensated by increasing stack height. At the same time, in order to compensate for the small storage capacitance, we had to significantly lower the beeline capacitance, which was done by introducing air spacer around the beeline, as shown in right side panel. Since our technological leadership will not stop at 20 nanometer, we are preparing next node DRAMs. Let me show you some progress in this regard. Next node DRAM cell capacitor is extremely challenging. So we need high compatibility of high K dielectric around high aspect ratio stack with thinner dielectric while minimizing leakage current. As you can see, left-hand side graph, we achieved greater than 95% step coverage even at 10 nanometer. And through work function engineering of high K dielectric, we can suppress dielectric leakage current even with EOT of 5 angstrom, which is shown right-hand side graph. Scaling of the physical dimensions has been more aggressive for NAND than logics or DRAMs. Currently, 16 nanometer planar NAND has been commercialized. However, as physical dimension decreases for 2D NAND, key design parameters such as the number of stored electrons and VT window decreases, while interference coupling between adjacent cells increases. At the same time, manufacturability decreases because of small process window. A paradigm shift from 2D to 3D structure can mostly resolve this issue. Interference coupling can be solved with gate-all-around structure of 3D vertical land. As you can see on right-hand side panel, the coupling-free nature of gate-all-around structure of 3D vertical land allows a single-step programming compared to dual-step programming of 2D NAND, which results in faster programming speed and lower power consumption. Furthermore, all of the knowledge accumulated from 2D NAND can be better applied to 3D vertical land. For instance, as you can see, bottom of the slide, 3D vertical land can hold multiple cells for more reliably than 2D NAND, which could help to push the limit multiple cell technology. We believe 2D NAND will only last for a couple of more generations. It will probably stop near 10 nanometer to give way to 3D vertical land, which only Samsung has successfully manufactured. 3D vertical land is currently being used in our leading SSD products. We started mass production of 3D vertical land with a stack of 24 layers in 2013, 32 layers followed in 2014. We believe eventually 1 terabit era will be realized. This means more than 100 layers have to be stacked. As of today, it's a big challenge, but I'm sure we'll be able to overcome this, as we have done in the past, through material and process innovation, as well as proper design technologies. As silicon process technology is fast advancing, so does packaging technology that will boost or complement performance of silicon. Packaging technology has been evolved in response to need for high performance, small form factor, and low power. The simple discrete packaging scheme is evolving to include more dies in a package as the case for die stacking and package stacking. A more advanced form of packaging would be TSV. TSV means through silicon via, which completely eliminates wire bonding for faster, smaller, and more energy efficient products. Let us look at some examples of advanced packaging. Packaging complexity increases as we add different ICs inside the package. A good example is on POP. POP means package on package, which has been commercialized since 2007. Our 2014 award-winning embedded NAND POP product, which is shown on left bottom, is only 1.5 millimeter thick. It contains an octa-core CPU, 4 gigabyte DRAM, and 64 gigabyte NAND in a single package. In order to minimize heat dissipation, thermal interface material is used between layers. And providing better electrical connection between layers, more bolts needed to be used, which will require to be finer than 0.35 millimeter. Finally, in order to deliver stable power to ICs, we have to minimize power noise by embedding capacitors. One of the most complex packaging technology involves TSVs. The concept of using TSV for advanced packaging has been around for decades. But it was only last year we have been able to see in real product in the market. This world-first 4-stack TSV DRAM product, shown on the left bottom, has 2.4 gigabps I/O speed. This was possible because TSV's interconnect length is only 0.2 millimeter compared to conventional 10 millimeter. Soon, by extending current limitation of 30 IOs to more than 1,000 IOs, we could increase total bandwidth to 1 terabyte per sec, even when each IO bandwidth is decreased from 8 gigabps to 2 gigabps. So far, we talk about basic technologies that will be used to realize small chips. Now, let us take a closer look at how these chips are being used in data-driven world through coming short video clip.
The CMOS image sensor in your smartphone is capable of taking high-resolution pictures with zero shutter lag. The taken image is loaded into the ISP inside the application processor. The ISP processes the raw data in order to remove noise and artifacts, which will give a high-quality image. Each Samsung AP has a distinct trait that can uniquely identify one from another. The image data from the AP is sent to the cellular modem. The image data is packetized inside the modem to be sent to the cloud server. The DRAM in the server receives the incoming data with the help of the virtual environment. DRAM sends the data to the server SSD, where it is securely stored. The stored image data can be retrieved to be viewed through your mobile or TV. The image data sent to the TV will be adjusted in order to match the resolution and frame rate. Then finally, the DDI simultaneously send the image data for it to be displayed.
I hope you enjoyed the video clip. We could see how CMOS image sensor, application processor, cellular modem, solid-state drive, and display drive IC were used. And now, let's look into the technical challenges and solutions for each component. As you saw in the video today, the data that is created and shared the most is video and image data, which are made by CMOS image sensor. Silicon scaling has also enabled CMOS image sensor technology evolution. CMOS image sensor has to fulfill the high resolution need, all the while conforming to strict form factor requirement of mobile applications. We are currently heading towards 1 micrometer pixel technology. At each generation, CMOS image sensor technology has dealt with the issue of decreased number of photons, which has been resolved by increasing sensitivity of the pixel. Increasing sensitivity through structural change was effective down to 1.4 micrometer pixel. The backside illumination scheme at 1.4 micrometer node minimized light scattering by placing metal layer below photodiode, which is exactly opposite to frontside illumination scheme. Approaching 1 micrometer pixel, not only sensitivity needed to be improved, but also crosstalk between adjacent pixels had to be minimized. Samsung isocell structure implemented a deep trench isolation which reduced crosstalk, as you can see in the simulation result on the right side top panel, as well as comparing image below. Isocell technology will enable us to break 1 micrometer pixel barrier of CMOS image sensor technology. Advancement in pixel technology can give new values to CMOS image sensor. There are many new technologies, but due to the time, I will limit myself to 2 examples. The first is global shutter. When you take a picture of fast-moving object, you will see what I call jello effect. This happens because of time lag in sequentially gathering information from the pixel. In-pixel global shutter resolves this issue because information is taken by all of the pixels at the same time. This is possible by temporarily storing information of the photodiode to storage element, which has been added in each pixel. Second is dynamic vision sensor, simply saying DVS. DVS mimics the human photoreceptor cells, which respond only to change in the scene. DVS are an event-based asynchronous operation rather than traditional synchronized frame-based one. Thus, it is able to detect fast movement. This technology will be useful for mobile, surveillance, and obstacle detection for drones. Advances in CMOS image sensor also demand high-performance processors for mobile applications. In fact, GPU performance of Galaxy S smartphone has increased 57 times in 5 years, whereas battery capacity only doubles. During the same period, smartphone thickness decreased by 30%, making it more difficult to dissipate heat generated by AP. Thus, it is clear that innovation in AP technology should not only come from silicon technology and circuit technology, but also from system architecture for lower power consumption. AP's power consumption is determined by capacitance, voltage, and frequency. As you can see in the middle graph, power and performance goes hand in hand. Therefore, providing just right power level to carry out the task would improve power efficiency. The well-known heterogeneous multiprocessing, simply saying HMP architecture, uses this concept, where workload is efficiently matched to the light cores. This scheme results in 20% power saving for video and gaming, and about 50% savings for listening to music. Power optimization has also been approached differently with the so-called dynamic voltage frequency scaling, simply saying DVFS. DVFS, which has long been implemented, uses a governor that determines CPU traffic level and sets the performance level accordingly to all IP blocks. More advanced, fine-grained DVFS assigns a governor to each IP such that performance level and traffic are matched in each IP. This scheme has been introduced in our latest SoC products. As you saw in the video before, many cases, we send out pictures or other data from our smartphone to elsewhere. You are seeing a large increase in mobile data traffic. Wireless communication technology is also evolving fast to keep up with this trend. In the long run, we'll need 5G mobile communication, which is targeting 6 gigabps to 50 gigabps in its peak rate. Compared to Samsung's recent cellular modem chip, which supports up to 450 megabps, this is about 10 to 100 times increase. Of course, it will bring much complexity to future chips. So, how can we achieve this data rate? Look at this Shannon capacity formula. Basically, it says system capacity increases the number of antenna, bandwidth, and number of cells. Space is limited for packing more antennas in a smartphone. What about the spectrum? Current cellular band is expensive and depleting fast. So, industry is turning their attention to millimeter wave, where frequency resource is abundant. But for its commercial adoption, high signal attenuation and power consumption has yet to be resolved. Last but not least, we can increase number of cells for higher spatial frequency reuse. In this direction, LT standards are enhancing many small cell-related features. This slide shows how silicon can tackle challenges in next-generation mobile communication. Take one step further into millimeter wave. Millimeter wave implies more propagation losses than current cellular frequencies. Here from this figure, we can see almost 20 dB more loss at 30 gigahertz compared to 3 gigahertz. To overcome this, millimeter wave system employs directive antenna array with 64 elements. With this, propagation losses dramatically reduced to level lower than that of 3 gigahertz as shown in the figure. However, such large array requires massive parallel processing capability that should fit in smartphone. We are certain that silicon technology can satisfy this requirement. By the time 5G is deployed, 10 nanometer technology will be ready to provide speed performance with much smaller form factor than current technology. Thus, we are prepared to support mobile data traffic increase of the future. Obviously, any kind of data traffic is burden to data centers. In data centers, high-speed storage is as important as computing power itself. After all, if an application cannot get the information it needs, that extra processing power doesn't have much value. This is why traditional HDDs are slowly being replaced by SSDs, where data can be accessed much faster. But in order to fully exploit the advantage of SSDs, a proper interface has to be developed. As you can see in this graph, early SSDs share the common interface with HDD, that is SATA. But SATA has some inherent inefficiency that cannot fully utilize low latency of PCI Express-based SSDs. The more recent NVMe PCI Express has designed to fully utilize the capability of NAND flash-based SSDs. Samsung has already commercialized world first NVMe SSD last year that had a sequential and random speed of 3 GB per sec and 750K IOPS, respectively. Our next 8-lane NVMe SSD will have double the sequential speed and world's fastest random speed over 1 million IOPS. In addition, SSD should be an enabling technology to help maximize server utilization by processing data within SSD. SSD devices already contain computing capability for managing itself. In-storage computing scheme attempts to use some of the computing resources inside SSD, which would have free CPU for other tasks. And because we minimize data movement, we end up reducing latency and power consumption. We have already tested this concept in our smart SSD, and result was 27 times performance gain and 3 times energy reduction. In the future, storage capacity expansion and performance improvement could be solved at the same time by just adding more smart SSDs. Whether your photo is saved in your personal SSD or in data center, ultimately, it will be enjoyed through a display, for example, TVs. Over the years, TV size has grown, and currently, we are seeing even 110-inch. This size increase requires improved resolution, as well as better color, and increased frame rate for smoother image transitions. As you can see on the screen, resolution increase will be 16-fold from Full HD to QHD. But data rate would have increased 48 times. Thus, high-speed data transfer technology for TVs is evolving as fast as any other field. Full HD TVs uses DDIs that handle 1.4 gigabits per lane, but for QHD, this will increase to 12 gigabits. But for 12 gigabits and over, it is necessary to implement next generation intrapanel interface. Next generation intrapanel interface requires complex serial link technology, which is used in high-speed wireline communication. In order to compensate for the high signal loss and remove signal reflection, next generation intrapanel interface should use various high-end equalization techniques, such as feed-forward equalizer, etc. All equalizers are systematically adapted for optimization for near-end, far-end DDIs. Thus far, we have reviewed the technologies that help to drive data-driven world. Now, I will talk a little bit about the security in the data-driven world before closing my talk. The downside of having so much information being shared among devices, including biometric, banking, etc., is that data is exposed to attacks. It might get abused or misused. The ultimate goal of security is to allow users to fully enjoy data service without any threat of data leakage. There are probably many ways to ensure data security. But today, I'm just going to briefly talk about Samsung's silicon approach. Our silicon approach is protecting every corner of the data path, such as creation, processing, transmission, and storing. Each small chip will have to be equipped with right security solution. For instance, inside the smartphone, our Exynos AP has DRM and secure processing. eMMC or UFS memory has secure storage. USIM has device and user authentication technologies. For sensors, data encryption is used for protecting biometric information. But going one step further, Samsung is preparing for actively make use of our physically unclonable function, simply saying PUF technology. PUF makes use of the fact each silicon has a distinctive process signature which makes it uniquely identifiable. Eventually, PUF will become the basis of anti-counterfeiting technology, and it can provide entirely differentiated security solution in the future. Now, I'm reaching to my conclusion. First, there is no fundamental limit in scaling down to 5 nanometer and probably below. Second, advanced silicon technology, advanced package, and chip solutions will provide better chips to data-driven world. Finally, data-driven world will continue and silicon industry will have more opportunity to thrive. Thank you very much for your kind attention.